You've probably heard of it. The number of transistors on an integrated circuit double every 2 years. Since the 1950s, every year we pack more and more of these transistors onto integrated circuits to try and improve the performance that we can extract out of them. Gordon Moore's principle has held up for several decades. However, in recent times, it's dying for CPUs, and a new type of computing has emerged.
Question is, what can you do when your computer is 1 million times faster? I have a lot to tell you, very little time, so let's get going.
Absolutely. Nvidia is the company that is sustaining Moore's law into the future. The goal of Nvidia is to accelerate the adoption of GPU computing before Moore's law becomes simply redundant for CPU. What is a GPU, I hear you ask? A graphics processing unit is a type of computing that does parallel computations on hundreds of cores instead of serial processing on the individual cores. Okay, that sounds a little technical, but I'll get into details later. What is important to note here is that Nvidia's type of processing, called parallel processing, is taking over the industry, and it's several times faster than relying on just a CPU. The GPU was solely invented for the purpose of video graphics rendering because a traditional CPU could not handle the large amounts of computations involved in rendering video games. However, in modern times, it has seen more applications than that, including AI.
We have reinvented computing for the first time since the IBM System 360, 60 years ago. There's $1 trillion worth of data center infrastructure installed in the world based on that old method of doing computation. Now we have accelerated computing, and we have the killer app for accelerated computing called generative AI.
This type of computing was solely restricted to video games in the past, and which is what Nvidia is well known for. However, in recent years, Nvidia, through different generations of their graphics cards from Tesla, Fermi, Kepler, Maxwell, Pascal, and the more recent, have morphed the graphics processing unit from just being a device that renders video games to a device that can be applied across a wide variety of industries, including data science and machine learning. Nvidia's first product was released in 1999 as the Geforce 256. It was simply marketed as the world's first graphics processing unit, a term which in 1999 Nvidia would define as being a processor capable of a minimum of 10 million polygons per second rendering. Laughable by modern RTX GPUs which can render billions of pixels per second, it also had low memory, only 32 megabytes compared to 24 gigabytes on top-tier graphics cards today. Let's take a moment to see how GPUs work in gaming. The object to be rendered is made out of triangles known as polygons. The polygons themselves are constructed out of vertices and nodes by a piece of software known as a vertex shader. Triangles are used to create the polygons onto pixels because they have the lowest number of points to connect, only 3. Rasterization is just the process of mapping the polygons onto pixels, where specific RGB values are applicable. The pixel shader will then provide each individual triangle with a specific color and texture. With the provision of a lighting source, it should basically transform our 3D object from being a bunch of triangles into a more realistic 3D looking object with reflections. On the physical side of things, GPU cores are much smaller and more plentiful than CPU cores, and they perform most of their computations by distributing a single individual problems across its many cores. Because of the fact that a GPU has many more cores than a CPU, it is naturally able to perform any computation faster that involves many repetitive tasks, and this is the type of problems that are involved in gaming. Rendering in gaming scenes involves solving a large number of matrix operations and the geometry of the 3D objects. This is perfect for using a large density of cores. And the physical diagram above, it shows a graphics processing unit with a much higher density of arithmetic logic units that are shown in green compared to the CPU. The GPU utilizes its large amount of arithmetic operations to parallelize the problem that it's solving compared to a CPU that only performs serial tasks. Scaling the number of cores on a GPU has continuously increased the gap between CPU performance and GPU performance. As in the diagram above, we can see the Nvidia graphics processing units versus Intel Core series CPUs. In 2007, Nvidia introduced an API application programming interface called CUDA, which stands for Compute Unified Device Architecture. The purpose of CUDA was to create a parallel computing platform that allows graphics processing units to handle general purpose computing. CUDA has enabled the GPU to perform majority of the heavy lifting from the CPU. It involves large numeric data such as computational fluid dynamics simulation, simulation of the global system of weather, and as well as biological modeling. Also, CUDA has extensions in high application programming interfaces such as TensorFlow, PyTorch, and Keras, which are used in the field of deep learning, which has had an exponential growth in the recent years. In 2017, Nvidia introduced one of their most notable products, the Geforce 1080 Ti. It was an enthusiast graphics card that was built on the Pascal architecture, which was the first architecture Nvidia introduced with mixed precision floating point operation. Geforce 1080 Ti was highly notable to gamers. However, its ability to perform mixed precision floating points meant that it had large speeds up in mathematically intense operations in linear and convolutional layers by using its tensor core. This essentially was the birth of hardware specific for machine learning. The Geforce 1080 Ti variants were a tour de force in computing, featuring a die with 12 billion transistors built on TSMC 16nm nodes and up to 11 GB of DDR memory. Nvidia never stopped to innovate on their core business, so in 2019 they introduced a more advanced architecture known as Volta, which replaced Pascal with the Nvidia 20 series. Volta had much faster tensor cores which speed up matrix operation in floating point computing. However, the big announcement for Volta was the introduction of real-time ray tracing cores on its GPU architecture. Ray tracing is a technique used for simulating the physical behavior of light as it reflects upon objects and casts shadows. The technique would generally involve tracking light rays as they move from a point of camera back to the light source, ignoring points which the camera may not be able to see, and creating a bounding volume which the camera can only see within. It may include such things as reflection, soft shadows, scattering, depth of field, motion blur, acoustic and ambient occlusions, and dispersion. Ray tracing creates very realistic image upon surface reflections. In 2018, Nvidia introduced the Turing microarchitecture for professional graphics processing units. The key elements of Turing were dedicated tensor cores and of course ray tracing cores for professional series of Quadro GPUs. The Turing architecture is named after the prominent mathematician and computer scientist Professor Alan Turing. In 2020, Nvidia announced their second generation ray tracing microarchitecture called Ampere. Ampere was built on TSMC 7nm FinFET technology for the A100 GPU die. However, for the 30 series, they used the 8nm process nodes on Samsung's 8N node. The microarchitecture also featured third generation tensor cores with BF16 and TensorFloat 32 and FP64. With the 30 series, the 3090 was the top tier graphics card, featuring up to 10,436 CUDA cores and up to 24 GB of GDDR6 memory. In 2022, Nvidia introduced the successor to Ampere microarchitecture with the introduction of Nvidia Ada Lovelace microarchitecture featuring 40 series graphics cards. Ada Lovelace microarchitecture features 4th generation tensor cores, 3rd generation ray tracing cores, plus shader execution rendering code SER. Ada Lovelace microarchitecture features up to 18,432 CUDA cores and up to 76.3 billion transistors.
Ray tracing, simulating the characteristics of light and materials, is the ultimate accelerated computing challenge. 6 years ago, we demonstrated for the very first time rendering this scene in less than few hours. Let's take a look at the difference in just 5 years. Roll it. This is running on CUDA GPUs 6 years ago, rendering this beautiful image that would have otherwise taken a couple of hours on a CPU. So this was a giant breakthrough already, enormous speed up running on accelerated computing. And then we invented the RTX.
By now you get the picture. Nvidia's chips are so advanced, they are now applicable not just to gaming, but across every industry that is adopting AI. In fact, Nvidia has about 95% market share of the GPU market for machine learning, noted in a recent report by Insights. In fact, Nvidia is putting more effort in developing data center hardware than gaming. The Nvidia GH200 Gray Swapper Superchip is a breakthrough accelerated CPU designed from the ground up for giant-scale AI and high-performance computing (HPC) applications. The superchip delivers up to 10 times higher performance for applications running terabytes of data, enabling scientists and researchers to reach unprecedented solutions for the world's most complex problems. The Grace Hopper superchip is actually two chips in one. It's a GPU plus CPU connected via a very fast bandwidth known as Nvidia NVLink C2C, which delivers a transfer rate of 900 gigabytes per second, which we call bandwidth. Grace Hopper combines both a CPU and a GPU. However, it is configurable to the demands of the data center it's being used for. The Grace is the CPU portion and Hopper is the GPU portion. You can either have Grace and Hopper combined together, or you can have the Grace CPU on its own, or two Grace CPUs, or the Hopper GPU or Hopper GPUs in multiple configuration. Speaking of the Grace CPU, it is designed for high performance computing, and it can deliver 2 times the performance per watt and 2 times the packing density and the highest memory bandwidth compared to today's servers. The bandwidth refers to the connection between two Grace CPUs. The combination of two Grace Hoppers creates a superchip that is specifically usable in HPC, high-performance computing, and cloud computing. The superchip is up to 144 cores built on the ARM architecture. On the other hand, Hopper is a GPU architecture that securely scales diverse workloads in every data center, from small enterprise to exascale high-performance computing and trillion-parameter AI. Hopper's main innovation is the use of advanced tensor cores with the transformer engine. A transformer engine is basically used to accelerate training workloads that are specifically related to AI models, especially those with large language models like ChatGPT, the recent AI that has taken over the world by surprise. Hopper has the ability to apply mixed precision floating points to dramatically accelerate AI calculations for the transformer model. Hopper triples the floating point operations per second over its predecessor, and the transformer engine combines 4th generation Nvidia NVLink bandwidth. As the recent surge in AI has proven that deep learning will be used across every industry, Nvidia is providing solutions from both hardware and software across every existing industry. These products include data center GPUs, Nvidia DGX platform, AGX platform, HGX platform, and networking solutions, as well as virtual GPUs. Their data center software includes Nvidia AI Enterprise, Base Command, Bright Cluster Manager, CUDA-X, Fleet Command, Mogul IO, Networking, NGC. Deep learning has been on an exponential adoption since the release of the large language model ChatGPT. Deep learning frameworks offer building blocks for design, training, validating deep neural nets through a high-level programming interface. Every major deep learning framework, such as PyTorch, TensorFlow, GAX, rely on deep learning SDK libraries from Nvidia to deliver high-performance multi-GPU accelerated training. As a framework user, it's as simple as downloading a framework and instructing GPUs for training. Nvidia boasts the advantage of being the most experienced GPU maker and the only GPU provider with advanced solutions that they have for deep learning in particular.
ChatGPT is a very, very big deal. Everybody's using it for different reasons, and everybody finds it delightful. That's its miracle. When was the last time that we saw a piece of technology that is so versatile that it can solve problems and surprise people in so many ways so often? Now, for a lot of people in the industry that have been working on this, we've been waiting for this moment. This is the iPhone moment, if you will, of artificial intelligence. This is the time when all of the big ideas about mobile computing and all that, it all came together in a product that everybody just kind of, I see it. I see it. I can now use this as an API, and I connect it to a spreadsheet. I connect it to PowerPoint. I connect it to a drawing program. I connect it to a photo editing program. It'll make everything better. Since ChatGPT came out, probably some 500 startups have already happened. And not only that, in about 2 weeks' time, they created applications that are really delightful.
Thanks to the rise in specific workloads trained on Nvidia hardware, in recent months, Nvidia stock has reached $1 trillion market cap, marking it as the first chip maker to cross the $1 trillion market cap. This is the story of Nvidia, the company that is taking over the world in computing.